So psi k square 1 plus vk square vk square is equal to beta k square 1 plus 2 times vk square. So I'm collecting terms. I put everything to the left-hand side and collecting terms vk to the 4 psi k square minus 4 times beta k square plus vk square, again psi k square minus 4 times beta k square minus beta k square is equal to 0. So I have so-called big quadratic equation. It is quadratic with respect to bk square, and if I divide by this coefficient, which is, by the way, positive, again, you see that psi k is equal to positive quantity plus 2 times beta k. Therefore, the square of psi k is bigger than 4 beta k square. So vk4 plus vk square minus beta k square over psi k square minus 4 beta k square is equal to 0. Solution of this equation, v k square 1 or 2 is equal to minus 1/2 plus or minus square root over 1/4 plus beta k square psi k square minus 4 beta k square. I have two roots, but remember, I said that this function, namely uk and vk, should be a real function. Therefore, I'm not allowed to take minus sign. Out of two roots, one is unphysical, because if I take minus sign, vk square will be completely negative, and therefore it's in contradiction with my previous assumption. Therefore, out of two roots, I select one, which is a physical one, and I put plus. You can rewrite it, so if I massage it a little bit, it's minus 1/2. Sorry, plus 1/2. I will put square root first. Psi k square. I will put. I will collect terms here. It's psi k over square root over psi k square minus 4 beta k square minus 1. So this is vk square. Let me for the moment introduce notation ek equal to square root over psi k square minus 4 beta k square. And this is not due to lack of the letters. You will see actually that at the end of the day these two letters are the same. Therefore I use the same notation. So this is 1/2 psi k over ek minus 1. So I don't put any modulus because I know which quantities are positive and they're all positive. Therefore there is no danger with that. And of course, uk square is vk square plus 1. So uk square is equal to 1/2 psi k over e plus 1. I will rewrite it several times. Oh, that's a bad idea. Well, anyway, I will recover. You have it in your notes, but I will recover. So, uk square vk square is equal to 1/4 psi k square over e k square minus 1. So this is equal to beta k squared over ek squared. I substitute ek, you see that it is positive with 4, 1/4 is cancelled. Therefore, uk vk, and I will call this quantity, is equal to minus beta k over ek. All quantities are positive. So, uk squared plus vk squared, another quantity which I need, is psi k over ek. Now you remember, my Hamiltonian was h is equal to E naught plus sum over k not equal to 0 psi k vk squared plus 2 times beta k uk vk, I know it by heart, plus sum over k. Here I have psi k uk squared plus vk squared plus 4 times beta k uk vk, b dagger k bk. So this was a Hamiltonian, and I already dropped off diagonal term using this condition. So this is E naught plus sum over k not equal to 0. Let me plug in everything. Psi k, here I have 1/2 psi k over ek minus 1 minus 2 times beta k squared over ek, this is this one, plus sum over k not equal to 0, bk dagger bk, and here I have psi k squared over ek minus 4 times beta k squared over ek. So you see, in fact, that this term is indeed ek bk dagger bk. This one is ek. Let's collect. So this is psi k squared over 2 times ek minus psi k half minus, let me write 4 times beta k squared over 2 ek. So when I combine these two terms, it is 1/2 ek minus psi k. So this is what is standing here. But anyway, I'm not interested in this term. It's just some constant which comes to E naught. I'm not going to discuss it in any details because I would like to concentrate on the spectrum. So, my Hamiltonian h minus E naught tilde is equal to sum over k not equal to 0, e k bk dagger bk, where ek is equal to square root. Now I will plug in psi and beta. When I open the bracket, look, will be epsilon chi squared plus 4 beta squared plus 4 times epsilon chi beta k, epsilon k beta k, minus 4 times beta k squared. So only first and cross terms exist. So this is epsilon k squared plus 4 times beta k epsilon k, right? Or let me put second term first. Now I'm plugging in everything. This is then u k over V times N times H square K square over M plus H square K square over 2M square. What can we see from this spectrum? We can see that for small k, let me for the moment write it as square root over c square hk square plus h square k square over 2m square. So, if the momentum is small, namely if chk is smaller than is larger, the momentum is so small that quadratic term is smaller compared to the linear one, is smaller than h square k square over 2m. Therefore, if hk is smaller than 2mc, I can drop the second term, and my epsilon k is equal to c times hk if hk is smaller than 2 times mc, or it's free h square k square over 2m if hk is larger than 2mc. So, if schematically I plot my spectrum, I will see that for very small momentum, so this is hk and this is epsilon k. For small momentum, it's just linear, and coefficient proportionality is c. And for large momentum, it starts to behave quadratically. So here one has chk, while here one has a free motion h square k square over 2. So what did we observe? We observed several very important points. First of all, the spectrum is gapless. There is no gap in the spectrum. Second, we started with weakly interacting particles characterized by quadratic dependence of energy as a function of momentum, and we arrived in the situation where the interaction leads to linear dispersion relation. So now C, this velocity, it's everything standing here. So this is u. Now let me put u equal to 0, n over v times m. And I have to say that this is square root. This is c squared. For the moment, non-weakly interacting particles with a short range interaction. Short range. C then equal to square root over 4 pi a h squared over m, and here n, and m once more time. So this is equal to h over m. Here it's n a, but I would like to multiply a square and divide a square. So you see that the sound velocity is proportional to square root of my guess parameter, small parameter of the problem. Here I have n a u, smaller than 1. And of course, it proportional to square root of the scattering length. So you see that appearance of this sound velocity is related to interaction in the system. Without interaction, we had free bosons, k square over m kinetic energy, and that's it. With interaction, we see appearance of phonons, because this is nothing but sound, the same kind of excitation which exists in solid state. So these are acoustic phonons, and their appearance is connected with interaction. We will see Friday that appearance of this sound-like spectrum explains the superfluid properties of the Bose gas. Therefore, the superfluidity is connected with the sound-like branch of the excitation. And you see that the system becomes superfluid only in the presence of interaction. Namely, we see it on Friday that without interaction, if we are dealing with that kind of dispersion, the system is not superfluid at all. So one needs to have interaction in order to make Bose condensed system to be superfluid. Okay, as I said, it's linear dispersion and it is gapless. And once again, there is very important message that transition to superfluid system is associated with existence of gapless excitations. And this is a subject of Goldstone theorem, which we will discuss in gross detail in magnetism. Goldstone theorem, which tells us that when in the system with a short-range interaction, continuous symmetry is spontaneously broken, then there exists a gapless branch of the excitation. So in the next lecture we will see what kind of symmetry is broken, and anticipating, I can say you that we already discussed that our Bose condensate can be characterized by unique wave function. In this unique wave function, we know that there is a modulus of the wave function and the phase of this wave function. The modulus of wave function is proportional to square root of the number of particles in the condensate. This is just T number. But phase is a variable. So we will see that the superfluidity is actually related to coherent properties of the phase. And since the phase exists on a circle and changes from 0 to 2 pi, we will see that existence of superfluidity in the system is associated with a spontaneously breaking discontinuous symmetry. So phase is living on the circle. And therefore, the existence of Goldstone mode is intrinsic property of this structure. However, at large momentum, of course, the system loses memory about interaction and behaves as a free particle, as it should be. So large momentums means short distances behaviors like for free particles. Let's make another comment. Let's make a comparison. Namely, I will do two simple estimations. One is for free Bose gas, quadratic dispersion, and one is for weakly interacting Bose gas. So you see that all effects are weak. And what I would like to estimate is number of out of condensate particles. Again, the same exercise. So free bosons. So number of particles out of condensate is integral d dk. I would, without losing generality, discuss dimensions 1, 2, and 3. So d small is equal to 1, 2, 3. And here it's Bose distribution function, epsilon k over temperature minus 1. So I already put chemical potential equal to 0. Epsilon k is quadratic. Therefore, for infrared part of this integral, I'm interested in very small momentum. I will expand exponent, cancel 1, and write it as temperature. Since I used the first term in expansion, it's a k to the power d minus 1 dk. This is Jacobian in d-dimensional system divided by k squared. K squared comes from the spectrum, which is describing free particles. So this is integral temperature times integral k to the power d minus 3 dk. So if d is equal to 3, you see I have integral from the shortest, smallest momentum, which is 1 over size of the system, to the smallest sizes 1 over a. A is the size of ball, and here it's dk. And you see that integral is converging. There is no problem. It's converging both on the upper and the lower limit. If d is equal to 2, and there is a temperature in front, then I have temperature times integral, the same from 1 over L to 1 over A. D equal to 2, it's integral dk over k. So this is temperature log L over size of the system. So you see that the number of out of condensate particles becomes divergent in two-dimensional system. Moreover, if I consider one-dimensional system, it's T integral dk over k squared from 1 over L to 1 over A. Then this integral diverges as a size of system on the upper limit. What does it tell us? It tells us that the Bose condensation is impossible in low-dimensional systems. Why? Because fluctuations destroy the condensate. The condensation can exist in three-dimensional system and occurs at final temperature. And this condensation is also coherent properties, long-range order. But the condensation cannot exist in two-dimensional system except for temperature is equal to 0, because log is still weak function. And the condensation cannot occur for one-dimensional system at all. Why? The same reason why phonons do not exist in one-dimensional system. The fluctuations are so strong that the condensate is destroyed. And this actually also the subject of theorem, and this is Mermin-Wagner theorem. Again, we discuss it when we come to the theory of magnetism, and there is very deep relation between superfluidity and magnetism. And theorem says that if system is characterized by short-range interaction, there is no long-range order for system associated with a spontaneous breaking of continuous symmetry for two-dimensional systems, except for temperature equal to 0, and there is no long-range order for such system in one-dimensional structures whatsoever. Now, we come back to interacting systems. So you see that spectrum is gapless, it's linear and sound-like, and the chemical potential is also 0. We don't have any chemical potential for our excitations. It means that these are like phonons. They are characterized by 0 chemical potential, quasi-particles. Creating a new quasi-particle doesn't cost you any energy. If we do the same calculations, putting linear dispersion relation, what we will see that now it's interacting. The only difference is here. So n is proportional T over C. Instead of k squared, I put k. It's k to the power d minus 2 dk. And it looks like that this integral is perfectly convergent in 2 dimensions. So it looks like that superfluidity is not suffering from the fact that we have low-dimensional system. And this is wrong. This is wrong statement. This is too naive to calculate the number of out-of-condensate particles. Actually, one needs to calculate density-density correlation function, and then everything comes to the proper place. Namely, the statement which I formulated with this very naive estimation holds for superfluid transition as well. Namely, the superfluidity can exist in 2-dimensional structures, only at temperature equal to 0, and cannot exist in 1-dimensional structures. And of course, when we are speaking in 2-dimensional, we mean the situation like film, where 3rd dimension is much smaller than 2 other dimensions, or when we are speaking about 1-dimensional system, it's rather quasi-1-dimensional, when 1 dimension along 1 direction is much larger compared to another one, like this piece of chalk. So this is again Mermin-Wagner theorem holds. But what we need to take home that in low-dimensional systems, fluctuations become strong, and one needs to deal with these fluctuations in a consistent manner. Okay, in the last 3-4 minutes, I would like to make the last comment. I promised you that I would like to make a comment, that I comment on the situation described by long-range interaction. Suppose now that we have a charged bosons which interact by means of Coulomb interaction. So UQ is 4 pi E square. Let me put E star, where E star is the charge of the bosons, over Q squared. If we look at this formula and plug in the interaction in this formula, what will we get? Epsilon k is equal to square root over 4 times p E star squared over times density. N over V is density. It's k squared h squared k squared over m plus h squared k squared over 2m squared. So what one sees that k squared in numerator and denominator cancel each other, and we have a gap. The spectrum is gapful, plus h squared k squared over 2m. If there is a contradiction with what I have said, no, because the theorem is not applicable for long-range interaction. And this interaction corresponds to UR is equal to E star squared over R. And this is long-range interaction. But interestingly, you will see that actually superconductivity, which is superfluid state of Cooper pairs, will also be characterized by the gap, but you should not be confused with that theory. In order to assume that, I supposed that my bosons are charged, but my bosons are well defined, namely that the typical size of bosons is still much smaller, much larger compared to typical distance. In superconductors, you will see that bosons are Cooper pairs, which are 2 electrons, but the size of this Cooper pair will be much larger compared to the distance between pairs. Therefore, speaking about isolated pair is a bosonic object is not a very good idea. And this charged Bose-gas formula describes the opposite limit, not the limit realized in the theory of superconductivity. What happens here, it's rather plasmon excitations. So delta square is what? Is 4 pi E square star n concentration divided by m, and this is nothing but plasmon frequency squared. So the excitations in charged Bose-gas are the same as excitations in charged Fermi systems without any fluidity, of course, which are bosons. And when we come to discussion of Fermi liquid with a Coulomb interaction, we will see how these plasma modes appear. And unlike this situation, as I said, in charged system, we have gap. But formula, since we were accurate deriving formula, still hold for that case too. Okay, I'm done for today. Any questions?
I saw that our diagonalization is exact, so the line from our particle is infinite.
No, we dropped quadratic terms. Look, the diagonalization was exact, but we dropped something from the Hamiltonian. What we have dropped will discuss, will define as interaction between particles, and will define as finite lifetime. What happens, and this is a very good question, and I forgot to comment, that the same effect that I discussed for sound velocity, namely here, can also be repeated for calculation of number of particles in the condensate subject to interaction at temperature equal to 0. As I said, for ideal gas, no interactions. All particles at 0 temperature are sitting in the condensate. However, here it's 1 minus. There is a gas parameter Na cubed over pi, I think, and this is 1/8, if I remember well. So the same time, the number of particles in condensate is not equal to total number of particles, even at temperature equal to 0. Yeah. So the interaction of particles lead to some decay of quasi-particles the same way as it happens in Fermi liquid. But at Fermi liquid, you remember this decay rate, 1 over tau, we showed that this is proportional square of temperature over Fermi energy. This is how particles decay at final temperature. In Bose gas, the same effect happened, but the power of decay is much higher. It is known as Belyaev damping. If I remember well, 1 over tau, this is Fermi liquid, in Bose gas, is something like temperature to the 5th power. But this can be done and can be calculated, of course, using more advanced method of perturbation theory based on diagrammatics. It will not be probably so easy to do it with UV transformation, because one needs to come to interaction between out of condensate particles, but the effect does exist. So the approximation which we used before we diagonalized Hamiltonian, namely we dropped processes where 2 out of condensate particles scatter from each other, is serious approximation. Apart of that, all the diagonalization procedure is exact. More questions? Okay, if not, next time we discuss superfluidity and see, probably next week we start with field of quantity. Yes.
He knows. Probably he knows.
And no, I think other than correcting because I don't have something else to do. Other than calculate the critical I score.
No, critical skill. Second lambda is 0.
Okay, then I go to the when this one go to infinity, so but I don't check it. Perito. Buona perito. No, there is something wrong. I didn't check it carefully.
Check this. I got lambda over 2 here. Where is this?
No,
No square, no square. We answer.
I just maybe I didn't check it.
Yes, check.
So maybe something wrong.
Okay.
I'm going to no, to ask him to delay the.
Yeah, no. No. Because I have to read all these things and I have to follow the other slide. I don't know. But
was good.
Yes, it was good. Because in Arabic it's plain each point. So we make it very clear why we are doing this and why we are doing it. So yesterday it was very fantastic.
But it's on this lecture's notes?
No.
Ah.
I think the directional part they didn't explain, but
Mm-hmm.
Naren used to explain everything.
Yeah, I have problem with my legs.
Even he proved why we are using Higgs, it's real H.
Mm-hmm.
And I remember one student asked me for one last time, why you put H is real and this. So when I ran he started. No one asked him and he proved it because he said this is real. He used to explain everything. He doesn't care you know or not, he just used to say.
we are coming to